Hi, I'll be talking about some R applications we are developing around AASC. This is something that has been going on for at least a year, and the idea, more or less, is to develop a few functions that will assist some of the users on getting information in or getting information out from AASC. A little bit of the background. You're aware, as most of you are statisticians, that R and the environment R has been quite widely used now for many applications. Many students, scientists are using it all around. But particularly, we've seen a large number of people in breeding using R for doing all their molecular or bioinformatics use, and of course to getting their breeding values and analyzing their breeding data. Now we have this tremendous flow of genomic data these last few years, and users obviously want to analyze this. But there is lots of difficulties. Before, we have issues sometimes preparing the phenotypic data and communicating that well with the pedigree data. But now we also have to communicate this with genomic data, so that it becomes a bit more extensive. And obviously, there will be potentially more complications that would make that your model doesn't fit very well. AASC, with all its capabilities for fitting linear mixed models, is a strong user base, particularly in breeding. AASC R in itself uses the environment R, which is an advantage in the sense that many people who are aware of the R environment can use it R directly before they go to AASC R for the data preparation and cleaning and so on. And obviously, once they have AASC R objects, they can extract the information for that. So most of the companies that use AASC R in their breeding programs, they develop pipelines. These pipelines are obviously code that they can develop within their own company, or they use other R libraries to do these tasks. So with this idea, more or less, is what we have as an objective to do these R applications around AASC R. So our main objective is to develop a series of routines and pipelines associated with it in the R environment to assist the user in their analytical needs. And this goes to use things for before they go to AASC and things that go after AASC. The focus mainly has been on use of genomic tools, because this is where we have seen the greatest needs lately that come from our users in terms of questions and queries and so on. So what characteristics are we looking for these sort of tools? Well, as I mentioned a bit before, we want R code or functions that will help prepare the data before we go to R, AASC R particularly, so this is upstream, or after we come from AASC R, which I call it downstream. So the focus has been mostly on what we have been receiving as queries and support calls from our users, and also some of the things associated with consulting and supporting different companies. So this has focused, as I indicated before, on the genomic part. We want to focus on these users that are the ones that are making these support calls. So its emphasis is mainly on breeders, people with limited R experience, or people with a bit more experience but want something a bit more automatic. The idea for us is to develop obviously efficient and tested routines that are sound statistically, and that they do some of the checks that are required, and obviously to facilitate all of this. And the idea is that they can be used directly around AASC R, or they can be used in other libraries or other pipelines that the same users might want to use later. So we want flexible functions that are compatible with AASC R, version 4 and onwards. And finally, one of the philosophies that we have taken is that we're going to use as much as we can some of the tested and widely used R libraries, and things like some of the graphics that we know are going to be much more efficient. So we don't want to really develop everything again. All of these functions, we want to make it as open as possible so people can modify them and use them, and us also we can eventually get improvements. So I'll talk mainly about ASR genomics. This has different models. I'll just mention a few things between a few of them. So the first model we're thinking about is something to kind of do this checking between the phenotypic and the pedigree data and some preparation. things about calculating the genomic relationship matrix for pedigree or for additive or dominance effects. We have functions that will check some of the diagnostic between these, for example, to check high levels of inbreeding, report some mistakes in the pedigree, and so on. We are aware these are available in many other libraries, but we're just putting it here together because this helps also to prepare some of the genomic data that comes forward. And the other section, as just mentioning, is just dealing with the genomic data per se. As user can come in different places, but we've been thinking about having a function that will do some of the filtering and reading of the molecular data in an efficient way, some form of imputations. We have simple imputations, but we can obviously go into more complicated imputation. And then everything else that goes associated with dealing with this molecular-based relationship matrix, so we can calculate them, A hat, D hat matrices, for additive or dominant effects respectively. Diagnostic that we did before for the pedigree-based matrices and some manipulations, but also some nice output like some PCA, cluster analysis, correlation matrices, and things like that. One of the things that we have as an interesting function is to pair the A pedigree and the A hat, so we can identify potentially, for example, where there's mistakes in the pedigree that are being accused by the genomic matrix. So these checks will be important. Some manipulations of this A hat matrix with the A pair on itself, such as blending and bending. Everything kind of getting ready for you to do obtaining the inverse of this genomic matrix on itself or combined with the pedigree as the famous H matrix from the single step GBLUP. And finally, obtaining your final inverse matrix that you can use directly into ASREMO. And then, obviously, you go on using HISREMO. All of this is kind of a priori things. In the next demo, I'll show you a few of those functions. I'll just briefly show you a few of the capabilities of ASR genomics and a little bit of the philosophy. I'm just going to read it, and the data set I'm going to use comes from an apple analysis. This is 247 apples that come from full sieve and half sieve crosses, so there's quite a good level of relatedness. They were genotyped, and we have a total of 2,828 SNPs. All of this comes directly in ASR genomics. So a little look up just phenotypic data. We have the name of the individuals in this vector, and then we have the family identified and father, mother, and then different response variables for these genotypes. The genomic data has 247 observations, genotypes. I'm just assigning here the names, and just to show you a few of these columns, this is already coded 012 and there's no missing data, but there could be missing data. We are just assuming that it's all genotype and there's being imputed, but that can change. So the first function that ASR Genomics has is calculating this genomic matrix. This calls different libraries and routines, and we put the data here, we request the method, and if we want to have missing values, how they were coded, and finally if we want this matrix in a sparse form to maybe be used by ASREMO or another system. So I'm just going to call this, everything is running in the back, and we can see a few of those records. Values on the diagonal are kind of close to 1, that's slightly different, slightly up and down than 1, and we have different relationships. A few are negative, but also we have this one that are close to 0.5 or 0.25, so this will denote full sieves or half sieves for these particular individuals. One of the main things we want to do is we want to assess the relationship matrix and assess its quality. So we have this function kinship summary that takes the matrix, and in this case is going to identify if we calculate the correlation of some individuals, it's going to be bigger than 0.95 according to the values in their diagonal. They will be identified to have some issues. So in this case, I'll use 0.95. And let's say, for example, elements that are bigger than 1.1 on the diagonal will be also of a bit of a concern because they might be too high in breeding. In this case, we don't consider they have too much in breeding. Other options is to clean the data and report final filter matrices. So just a little bit of a report. These are the values on the diagonal, values on the off diagonal, 0.29 and 1.06. So we have some elements that are quite high in the off diagonal. The mean values on the diagonal is slightly lower than 1. And then the everybody off diagonal is around 0 really. So there's 25 observations that have values bigger than 1.1 and 5 observations that are suspicious to be duplicates, so we can decide to eliminate or not. We have graphs. Here is just a graph of the diagonal where you see the whole range to see what's going on. So a few individuals that potentially will have some level of inbreeding. Values on the off diagonal, it makes a lot of sense. A big cluster around 0.5, then 0.25 for half-sieves, but most of them are around 0. That makes a lot of sense for this data set. The individuals that are reported as potential duplicate, here we have their actual names, so we can assess if they are actually duplicates or not, or there's another issue on their parentage or something. In this data set, it is quite possible they are actually the same, even though they belong to different families because of errors and mislabeling. And then also a few of the high elements on the diagonal. We have one individual with a value of the diagonal of 1.7. Just a simple little quick fix. We'll just take 98% of this G-hat matrix and blend it with a 2% of a diagonal or identity matrix. Later on, we have functions in AASC genomics that will do some of this correction, and we assess the quality of this and then tweak them in blending or bending. But in this case, I'm just doing a very simple averaging just to show you that I can recalculate this G-hat matrix, now called G-hat B. We have different summaries, but now we don't have values that are as high on the off diagonal. Also, there's been some tweaking on elements on the diagonal value and the relationships. We still have some individuals that are being reported to have correlations bigger than 0.95, but in this case they are lower. They're just being 0.98 except for one. And this is pretty good. It's looking like the matrix has a bit more stability. Elements are still on the off diagonal that are quite high. And things we can do here, for example, this is another function that we have. It's called kinship heap matrix. It will take this G-hat B matrix and provide us with another way to kind of assess how this genomic matrix is behaving. And you can see here, these little squares are full sieve families. And then we have some relationship between some of these individuals in a second or third generation ago. So we can see the grouping a little bit. So this will actually provide us with some information about this population and to assess if it really is what we think. This function, kinship PCA, is going to get lots of different matrices of information that we can use, for example, for a GWAS. But I just want to show you not all the output, but one of the interesting outputs here is this PCA. I have requested the PCA with the option groups, where we have different colors by group. And you can see the family structures, and some individuals are off the family structure, which might denote that they have some mistakes on genotype or in assignation or labeling, as I indicated before. So this data set actually requires a little bit of cleaning probably on terms of what the families are. And there is another graph that comes here, which is like the script plot in order to assess how many dimensions you can use for a GWAS and so on. Now, I'm happy with my matrix, and just to show you, we can proceed to solve later in AASC genomics. We will have different ways to invert this matrix, some more efficient than others in terms of use of memory. So I can just get the inverse of this matrix, and you can assess here, this is the inverse of that matrix, G-hat B. And finally, I can call the function full to sparse, that also in our library, and just will provide us with this matrix, which in a sparse form that we can save and then send directly to AASC to analyze and to perform some GBLAB analysis. This is just to show you a little bit of the idea and the concept that we can do. Well, after that demo, I just want to close with a few more little things. One of them is that we have another library. I'm not going to present this. This is called AASC Tools. They're using the same philosophy as the AASC Genomics, but in this case, the focus is mostly on having some functions, mostly for modeling tools, and some graphical output also. Again, with the same philosophy of helping before and after you use AASC. We have been focusing strongly on the needs of the plant breeders. So, for example, I have a few of the functions here about fitting a set of spatial analysis. In this case, the user indicates some of the main variables and the model will be fitted in a semi-automatic way. We have implemented a special model selector for augmented and replicated designs. We have a special model selector for replicated designs that has a pre-identified set of around 32 different spatial models. Each of those models is fitted, and then you get goodness of fit statistics for this spatial analysis, and then from there, obviously the special model selector can make some selection or use some of your actual selection. Following those spatial models, what we do is we store the predictions and we store weights if you want to follow that into a two-stage analysis with weights. Obviously, we need to do that for each of the trials, and then we check for audit in this case if there's enough connection between the sites, and then we can perform the MET with a typical factor analytic of different orders or a core GH, etc. And the outputs are from these two-stage analysis are stored, and then we have different functions to explore this output, like the typical PCA, biplots, and stability indices. We have other models that we've been developing, so a basic animal model with some pre-selected options, so it's just limited, more useful for animal breeders in this case, where you only have like one covariable and a couple of random effects. So again, as I mentioned, I'm not going to show much of this, but it's things again to support the use of AASC. Finally, something that we consider very relevant is using some of these libraries and functions in a system that is more like interactive. And again, to bridging this gap between users that are not very familiar or comfortable with R and something that is a bit more interactive. A web interface we consider is something very relevant. We don't have too many things developed with this, but we're in the process of doing some. So we have R Shiny and the React.js applications that communicate very well with R, so we can communicate there and get the output and send the data and so on. And users have shown and indicated to us that there's an interest to have also not only on their own computer, but having cloud systems that they can access, let's say from their own facilities, greenhouses, or some of their, even in the field, to perform direct analysis or consult some of their data. We think this gets very well with breeding management systems, where you can communicate with the data or update the data there, or actually just extract it so to do your own analysis at some point. And one of the things we like about having these systems on a web application is that if you use some of, like, for example, Amazon Cloud, you can scale up your memory and then perform, particularly for molecular data analysis that are more complicated. And finally, with these web interfaces, you can do whatever you want to make it suitable for the own user. In this case, for example, translate it to a different language, put the logos, and have the procedures with the actual names that are common for the company. There is a little bit of things here to do that will be interesting, and they can use some of the libraries I just mentioned. So in summary, just going briefly, where linear models have gone a long way, and we are aware of all the benefits of fitting linear mixed model for breeding, we have plenty of challenges ahead with analyzing molecular data, doing all this genomic selection or GWAS analysis, and they're becoming more and more common in different breeding programs. So it is time that we kind of help our people we help in terms of our statistical support. We have the software, we have flexible, fast, and accurate software with really sound statistical background to fit these models, but sometimes it's hard to reach the users. So we need to kind of bridge this gap and make it easier for the users, in this case thinking more about breeders or people who are not very familiar with R. That's where some of these applications could assist to not take away the control from the linear mixed model, but to limit it in a way and to exploit the output that will make it this much easier and possible. And finally, obviously, I mentioned about the web interfaces. These are going to be very good things, again, to bridge even more this gap to users that will not necessarily know R is behind all of their routine analysis. So my work is not just myself. We've been working with Amanda, who is helping us from Brazil, and Darren, who is helping from BSN in England. This has been a very good work in terms of adding things. We don't have the product totally finished to show you to distribute, but just in a few more months we think we'll have something that you can play with and we'll be happy to receive all your comments and suggestions. Thank you.